In this lesson, we are going to be doing a Eastern Cape paper that was written on the 16th of April 2021. It includes a little bit of paper 1 content and paper 2 content. Please look out for the download that I've attached so you can download the entire exam paper, which also has the memo, so you can follow along with me. In question 1, we are given a geometric sequence, and the first question says calculate the value of the fifth term. So we just need the basic geometric formula. And so to find term 5, we can just say term 5 is equal to a, which is the first term, which is 10. Now to work out the ratio, you can just take term 2 divided by term 1, which is 5 over 10, which is a half. So that'll be a half to the power of n, which is 5 minus 1, on the calculator, which will give us 0,625. So that's going to be the fifth term in the sequence. Then for number 1.1.2, they say determine the nth term. So that you just use the formula again, but you don't fill in a number for n. So it'll just be a, which is 10, r is a half, to the n minus 1. And that's the answer for number 1.1.2. And then 1.1.3, explain why this series, you see, did you guys know that a sequence is whenever they have the semicolons? And then to call it a series, they just put pluses in between. That's all. Now, why does the infinite series exist? Well, an infinite series exists when you have two scenarios, where you have to have both of these. It has to be geometric. So it is geometric. And the ratio must be bigger than minus 1, but it must be less than 1. So this ratio, our ratio is equal to a half. So it is between minus 1 and 1. So in the exam, you could say something like, it is geometric, and r is between minus 1 and 1. For this question, you need to know that there's a very important mathematical property with patterns. And that is the following. Let's say I've got the sequence 3 plus 5 plus 7 plus 9 plus 11, for example. If I work out the sum of 4 terms, then that's going to be 3 plus 5 plus 7 plus 9, which is 24. If I work out the sum of 5 terms, that'll be 3 plus 5 plus 7 plus 9 plus 11. And that's going to give me 35. What's amazing is that if I say the sum of the first 5 minus the sum of the first 4, it's going to give me 35 minus 24, which is 11. Now this makes sense because all of these would cancel, and you'd only be left with this last piece. So what I'm trying to show you, oh, and 11 is term 5. So what I'm trying to show you is that if you want to find term 5, you can say sum of the first 5 minus the sum of the first 4, and that'll give you term 5. If you want to find sum of if you want to find term 30, then you say sum of 30 minus sum of 29. If you want to find the term of 13, then you say sum 13 minus sum 12. If you want to find the general formula, Tn, then you say sum of Sn minus Sn minus 1. One more, term 15, you would say S15 minus S14. See that? That is a mathematical property that you need to know. So if we want to find term 20, we can say that term 20 is equal to the sum of the first 20 minus the sum of the first 19. So the sum of the first 20, let me do this as a little side calculation. The sum of the first 20 would be equal to, so you just plug in 20 in the place of p. So it'll be 20, 20 plus 1, 20 plus 2. And on the calculator, that'll give us 9,240. Then if we find the sum of the first 19, then you just plug in 19. 19 plus 1, 19 plus 2, and that'll give you 7,980. So we can now say that this is 9,240 minus 7,980, and that's going to give a value of 1,260. And so that's the answer, 1,260. In this question, we can definitely see that we're probably going to have to use the sum to infinity, and then this part here will be pretty easy. So let's start with this first part. So what we need to do is we need to know A, which is term 1. So let's go find term 1. To find term 1, you just start with whatever number is at the bottom here. So that's going to be a third to the power of 1, which is just a third. Then you also need R. So to find R, we're going to need to find term 2. So term 2, you'll just say a third to the power of 2, which is 1 over 9. And then you can find R by saying term 2 divided by term 1. And that's going to be 1 over 9 divided by a third. And if you eventually do that on the calculator, that will give you a third. So R is a third. And so we can easily go work out the sum to infinity now as a third, which is A, over 1 minus R, which is a third. And if you work this out, we get a value of a half. Okay, so we've done the sum to infinity. Now for this one, quite interesting. So this one's really interesting. So to find term 1, you plug whatever this number is into here. But the thing is, there is no k over here. So guess what, guys? Term 1 is 5. Term 2, also 5. Term 3, you guessed it, also 5. Term 4, what, are you a mathematician? Yep, it's also 5. So we're going to have a whole lot of 5s, but now what some students would do is they'll say, oh, okay, so there's going to be 40 of them. No, no, no. Remember, the number of terms is always the top number minus the bottom number plus 1. And so there's actually going to be 39 terms in that sequence. So there's going to be 39 5s. So if you have 5 plus 5 plus 5 plus 5 plus 5, 39 times, then you can work it out as 39 times 5. And that's going to be 195. So now we can finally work out the answer, and that final answer is going to be the sum to infinity, which was a half, minus the 195, and that will give us minus 194.5. This question is part of a 16th of April 2021 Eastern Cape exam paper, and I'm actually going to disagree with the memo, and I hope that by going through this with me, you will see what I mean, and potentially you might even agree with me. So we have this person, and I think it's pronounced Atlahang, generates a sequence which he claims that the sequence can be arithmetic and also geometric if and only if the first term in the sequence is 1. Is he correct? Now the memo goes on to say that he is correct, because if the first term is 1, then you would do this. Or first of all, for arithmetic, we know that the first term is A. Then the second term is A plus D, and then the third term would be A plus 2D. So if the first term is 1, then they're saying 1, 1 plus D, and 1 plus 2D. Then for geometric, they go, it goes A, and then AR for term 2, and then AR squared for term 3. Now, if they're saying that the first term is 1, then that'll be 1, R, and R squared. Now, they're saying here that the sequences, well, he's generating a sequence, and it can be arithmetic and geometric, but it's the same sequence, so it means that this part is the same, but that's obvious to see. But then these two would have to be the same, so let's say that, because it's the same sequence, so 1 plus D is equal to R, and then these two would have to be the same as well. So we can say 1 plus 2D is equal to R squared. So we can do some type of simultaneous equation over here. So we know that R is 1 plus D. So I'm going to put that into the second equation. So 1 plus 2D is equal to, now R is 1 plus D squared. And so if I had to go multiply that all out, I would eventually get the following. And what you would eventually find here, if you solve, is that D squared is equal to 0. And so if you take the square root, D is 0. Okay, great. Then you can plug that D back into here, or more like over here, and you would find that R is equal to 1 plus 0, which is equal to 1. Okay, so R is 1, D is 0, everything looks great, so it looks like this guy is correct. But guys, there are so many different ways we could have done this. What if the first number is 2? Let's make the first number 2, okay, and let's see what happens. And I just want to quickly show you that if D is 0 and R is 1, then the sequence would look like this. It would be or a we knew was 1 already, so it would be 1, and then 1 plus 0 is 1, and then 1 plus, so the sequence would just go like this. So I can see, yes, it is arithmetic, because you're just adding 0 the whole time, so that is technically arithmetic. But it's also geometric, because you're multiplying by 1 to get to the next term. So everything looks okay. But what if the first term is 2 instead? Okay, then it's going to be 2 plus d, 2 plus 2d. And for the geometric, it'll be 2r, and 2r squared. So now once again, these two parts are the same. And secondly, these two parts are the same as well. So we can go make equations. So we can say 2 plus d is equal to 2r. And then over here I'll say 2 plus 2d equals to 2r squared. So now I'm going to get d alone in this equation. So we'll say that d is equal to 2r minus 2. And I'm going to plug that over here. So that will be 2 plus 2 in brackets 2r minus 2 equals to 2r squared. Then going to multiply in. And I'm then going to take everything to the right hand side. And that would eventually become like that. I'm going to divide by 2, so we just get r squared minus 2r plus 1. If you had to go factorize this, you're going to get r minus 1 and actually another r minus 1. And so if you had to go solve for r, you would get that r is 1. Then you could plug that r back over here, and you would find out that d is equal to 2 times 1 minus 2, which is 0. Okay, so we're getting the exact same answer that we got earlier. And so what would this sequence look like? Well, it would be 2. And then if r is 1, it will just be 2. And so it's just going to be 2, 2, 2, 2, 2. So that is geometric, because you're multiplying by 1 each time. But it's also arithmetic, because you're adding 0 each time. So I completely disagree with this person who says that the only way you can get geometric and arithmetic is if the first term is 1. There are thousands of different ways that you can do that. So in the memo, they say that he's correct because they start off by doing the way we did in the beginning, and then they show that it works. So I do agree with that, but it's not the only way. So it's not the if and only if. So I would say no. So this often does happen where the memo is actually wrong. I mean, it doesn't happen that often, but I have seen it from time to time. So I disagree. In this question, we are told that they give us QT and TV, but that's already been filled in. But then they say that TR is 8 units. So that's this entire length. So it's quite weird, but not drawn to scale, obviously. So this length would only be 3 units. Because the whole of TR is 8, and this is already 5. So it looks a bit weird, but these diagrams sometimes aren't drawn according to scale. So we need to work out QS over PS. Now, that's quite an easy one using the proportionality theorem, because if you look in this triangle here, we've got these parallel lines over here, and so we can easily say in triangle QVP, can say that QT, well, let's start with what we want. It's QS over PS is equal to QT over TV, and that's just going to be prop theorem, because lines TS is parallel to VP. Now, that's not the only reason that you can give. There are others. The other one is line parallel and then side of triangle. Okay, so I've seen those two different reasons. And so we can go fill this in then. QS over PS is equal to QT, which is 3, over TV, which is 5. Okay, so that's number 2. So because we got that, I'm going to go fill in these ratios that we just found. But now those are just ratios that we found. So we can't say that this is now a length of 3 and this is now a length of 5. We could rather say that this is 3x's and 5x's, for example. We didn't go find the exact length. We just found the ratio. Now, for 2.1.2 says the area of triangle PQR, okay, so that's the entire triangle, over the area of a quadrilateral PSTR. Wow, so this looks quite interesting. So I must be honest, I had to sit and look at this question for quite some time. Because I was trying to work out the area of the quadrilateral directly, but there is no way to do that. So the better approach is actually to do the following. It's to realize that the area of this blue quadrilateral is the big triangle minus the small triangle. Can you see that? It's the big triangle minus this smaller triangle. So let's go work that out first. So the area of quadrilateral PSTR, or PSTR, is equal to the area of triangle PQR minus the small triangle QST. Pause the video if you need to and think about what I've just said. I'm saying that it's the big triangle minus this little piece. That'll give you the area of the quadrilateral. Now, to try keep the number of variables to a minimum, I want you to realize that this triangle and this triangle, they both share this common angle Q. So let's use that common angle Q. So we can say that that's going to be equal to the area of PQR. So the formula that I'm going to use is area is equal to a half AB sin C. You know that formula. So it's going to be a half. Now for PQR, and we're using this angle, you're going to take this length, which is 11, and then you're going to take this length, which is 8x, and then you're going to say sin of angle Q, and then you're going to say minus the area of this little triangle QST, which would be a half times by 3 times by 3x, and then also times by the sin of Q. Now, you can go multiply all of these numbers together. It's going to give you 44 sin Q. Oh, but there's also an x. 44x sin Q minus 4.5x sin Q. But now these can be minused from each other because they both have a sin Q. And so that can become 39.5x sin Q. So that is the area of the blue triangle, or the blue quadrilateral. So now we can actually go fill this in over here as we know that the area of the quadrilateral is 39.5x sin Q, and then the area of the triangle PQR, we already looked at that over here, so that's this one, so that means it's this one, 44x sin Q, and then all of a sudden the sin Q's cancel, the x's even cancel, and so we're left with 44 divided by 39.5, and then on the calculator you're going to get 88 over 79, and to 2 decimal places that'll be 1.11. So that's quite a difficult one. So in this next question, the important things I would want you to see is that there is a tangent, okay? They've told us that the tangent is this one here, so look out for that. Anything else that's important? Oh yes, this is important. AE is equal to AB, but they have given us that on the diagram over here and over here. And then these lines are parallel, but they have showed us that. Okay, so good. There's nothing we're missing there. Oh, and I nearly didn't see that. A1 is equal to x. So let's actually go call it x. Now, in question 2.2.1 says, give with reasons 3 more angles equal to x. Okay, so the first one's quite easy. And by the way, if I was you, I would definitely pause the video and try these yourself. Even if it takes you 20 minutes, it's so much better doing it like that compared to sitting and just watching me. Trust me, trust me, trust me. So, okay, so the first one I would see is that there's an alternating angle over there. So we can say that angle D3 is equal to x. And that's just because of alternating angles due to the fact that lines AB is parallel to line ED. Okay, so that's x. Then there is a theorem that hardly ever gets examined, but when you have a circle and you have 2 lines that have the same length, then they will make angles that are the same. So look at this line. Which angle is it making? Well, it made angle D3. Now look at this line, so it's this one here. What angle would that one make? So what you do is you almost pretend that you put your finger over here and you put your finger over here, and you try bring your fingers, you try to bring those 2 green dots to a single corner. So if you look carefully, they'll be able to both go there. So they'll be able to meet over there. And that's angle D2. So D2 is going to be the same as D3. And so we can say that angle D2 is equal to D3. Whoops, D3. And that's because of equal chord, equal angle. It's a theorem that doesn't get used that often. Or in fact, let's say equal angles, like that. Equal chord, equal angles. Okay, so we have found 3. Now, the next one is, if you look at this tangent over here, whenever there's a tangent, my advice to you would to always be, look out for tan chord theorem. So the tan chord theorem, if you write that out, tan chord, you need a tangent, which we have, and you need a chord. So here's a chord, for example. Well, let me make that a bit neater. There we go. So we've got the tangent and the chord. Let me make that even neater because I can't even see that letter. Now, look at the angle in between the tangent and the chord. It's this angle over here, D1. Now, take your finger and put it on the ends of the chord and try to make those two green dots come together at a corner. Now, some of you might have gone this way. That is correct. It is coming to a corner, but it has to come to a corner inside the circle. So you would rather go this way, and so there they would meet over here at angle A1. Now what the tan chord theorem tells us then is that this corner angle, which is in between the tangent and the chord, is the same as this one. So that is our third angle. So we can say angle D1 is equal to angle A1, and that's because of the tan chord theorem. Great, so that is the 3 different angles that we needed to find, and I would definitely label those on your diagram. Oh wow, check that guys, it's all these ones over here. So I would definitely label that on your diagram just in case we're going to need it for the future questions. Okay, so moving on to question 2.2.2, which is a similarity question, and it's to prove that triangle DEA, so let me highlight that for us, DEA is similar. Sorry guys, I just realized I wasn't showing you the marker location. So the first one was only 3 marks. Now this one's only 2 marks. Oh my word, 2 marks for a similarity. It must be super easy. And then DBC. Okay, so we have to prove that those 2 triangles are similar to each other. Okay, so what I've identified, I don't know why it's 2 marks. I'll be honest, that's quite a little bit of marks. It's quite weird. This structure here is a cyclic quadrilateral, right? And we should know that the angle on the outside is always equal to the opposite interior angle. So we can say that angle B2 is equal to angle E. And that's because of exterior angle cyclic quad. Okay, so B2 is equal to angle E, so then we're pretty much done, guys, because we already know that D1 is the same as A1. We already saw that, so we can just say that D1 is equal to A1, and that was already proven. And then remember that the third angle is always going to be equal to each other because of sum of angles in a triangle. So which angles haven't we used? Well, we haven't used D2, and we haven't used angle C. So we can say that they're the same, and that's just because of sum angles triangle. If you did this in a different way, it's absolutely fine. There's usually more than one way that we can do these questions. So now what we can do is we can say, therefore, these 2 triangles are similar to each other, DEA. We don't have to worry about the order because they've already given us the question, and so that means the order is correct. And then we can say angle, angle, angle. So now we are moving on to 2.2.3. Now what I typically do first when I get a question that looks like this is I usually look at the previous answers with the similarity and I make those ratios. So we already know that triangle DEA is similar to triangle DBC. We've already proven that earlier. And so because of that we can make these ratios. DE over DB equals to EA over BC equals to DA over DC. And the reason for that is similar triangles. I used to say corresponding sides in proportion, but I've started using this one as it's a lot faster. Okay, then what I would do is now hopefully this is going to give us our answer. So I would go circle whatever I'm looking for. So I'm looking for DC. So there I've got a DC. I'm looking for BC. There's a BC, a AD, and a DB. Okay, so that's not really the best looking thing, because usually you would want it to be something like this. You would want it to be all four of them are together like that, and then you would just do cross multiplication. But here we have a bit of a split. So I have a feeling that we might not be able to get the answer directly from that. And so what I think we can maybe do is, this doesn't seem like it's going to help us. Okay, so let's scrap that idea. But I usually start there, because usually, like 90% of the time, that would have worked. But not today. So then what I would do is I'd go look at DC, and I would be like, okay, DC is over there. BC is there. AD is this one. And DB is this one. So we could prove two triangles similar. Now we have options here. We could maybe prove this triangle similar to this triangle, but I don't really see that working out that nicely. What I would rather do is, let's go with this triangle. And I'll be honest, I tried these two triangles earlier, or just now, a minute ago, and it didn't work. It didn't work at all. So maybe you tried that and you realized the same thing. So what I would rather do is look at this triangle, and then the big one around that. Now what's nice about that is we can see that these angles are the same. So that's already one thing. And then they also share a common angle. That is why this one works so nicely. So you need to explain to the person marking your exam which triangles you're working in, because they haven't told you which triangles to work in. So it's triangle DBC, which is the small green one over here, and triangle, then the big pink one is ACD. Now the order doesn't matter for that step. Okay, I'm going to start with the green one. So I'm going to say angle C is equal to angle C, because those are common. So that's that. Then angle D1 is equal to angle A1. That was already proven earlier, so we can just say proven. And then the only other angle that we haven't used in the green one is B2. Now that, or I'm not saying that it's 90, sorry, I made it look like that's 90. I'm saying this one is the same as the other angle that we haven't used in the pink one. So we've used this one in the pink one, and we've used this one, but we haven't used this one. So that's going to be ADC, angle ADC, and that's just because of some angles in a triangle. And so then we can say, therefore, triangle CDB is similar. See how I just used these three letters here? And then that's similar to CAD, using these three letters here, just to make sure that I get the order correct. And the reason for this is angle, angle, angle. Now, I hope we're going to get lucky, and what we're going to do is we're going to take these three things and we're going to go make our ratios, and we hope that we'll be able to get this from that. So we can go make our ratios now by saying that CD over CA equals to DB over AD equals to CB over CD, and the reason for that is similar triangles. Okay, let's see, guys. So DC, where's DC? Ooh, there's two of them. That's quite interesting. That might not be a good thing, but let's have a look. DC and DC. Yeah, I actually don't like that. But sorry, I'm jumping the gun here. And then we've got, they want BC, so BC, yes, we have that one. And AD, yes, we've got that one. And DB. Oh, okay, so I see what's happening. We don't need this one. We can ignore that one completely, and we can just go with this one over here. So we can say DB over AD is equal to CB over CD. And then what we do is we get DC alone, because that's what they want. So to get DC alone, I would take it to the top. And then I would multiply the AD across. And then finally, I would divide by DB. And there we have it. So we did it, guys. So I originally, remember I told you earlier, I started by trying to prove, because it seemed logical to me that we try prove this triangle is the same as this triangle. But then I got super stuck. There was no way for that to work. So then I thought, okay, fine. Then maybe it's this triangle and then the big pink one. And what's nice about that is that they share a common angle. So that's an easy way to get an angle, right? Okay, so that's question 2.2.3a. Right, now the next one is B. So once again, whenever I see something like this, I would use any similarity that we've done already. So earlier on in 2.2.2, we did similarity, which was DEA, and I will not forget that. I'll always come back to those types of things first, before I even get involved in the question. I would always try to find a little hack. So I would try and make these ratios, so DE over DB equals to, and these are two triangles that we proved similar earlier, but sometimes these examiners are sneaky, guys. We've got to catch them. And then that's just going to be similar triangles once again. And let's see, maybe we're lucky. So EA, yes. DC, yes. DE, yes. And AD. Okay, doesn't look great. It's all split up. You see, because normally we would like to have 4 of them in one, but this one's giving us a split one again, which isn't great. And then I must also remember, though, that we also proved triangles similar in this previous part. Now, I can't remember the order that I used, but I think it was something like triangle CDB was similar to triangle. Remember, we did it just now, guys. We did this little one, and then we did this big one. Remember, we did that a few seconds ago. So I just want to remember that as well. So what was it? C went with C, D went with A, and then B went with D. I remember that. Okay, so let's try that one. Maybe we can get lucky there. So I don't think so, though, because there's an EA, and we're definitely not going to get an EA out of that. So yeah, I'm feeling quite stuck. But that's okay. That's normal for maths, right? It's about problem solving. So I'm going to sit and give this some thought. For you, it would be great. Pause the video. Give this a try, guys. Never go to the memo, or don't fast forward the video. Give it some thought. You'll get better at maths like that. Unless it's 3 o'clock in the morning right now and you have an exam tomorrow morning, you better fast forward that video quick so you can get some sleep. Yes, that's me being silly with my little jokes. Alright, so back to my focus. So because none of the triangles that we have already proved similar are working, none of these ratios are working, so I'm going to cancel that all out. Wow, this question's been a bit of a challenge. Then what I do is I restart. I go back onto the diagram and I'm like, okay, fine. I'll go prove more triangles similar. I don't know how many triangles they want us to prove similar in this question. And only for 3 marks. Pretty crazy. Anyway, so EA, I would go find EA. Here it is. DC, where's DC? Here you are. DE, there you go. And AD. But I just realized that that's just going to take us back to proving, it's going to take us back to proving that these 2 triangles, this one and this one, but we already did that in question 2.2.2. So it wouldn't be that. Oh, guys, I've just seen something. Earlier on, when we wrote out these little ratios where we said DE over DB equals to EA over BC equals to DA over DC. Remember, we said that earlier. Then what we did is we went and circled these, and we got that this one and this one and this one and AD. So we said there was a bit of a split, which wasn't very nice. But then what I realized, and I'll be honest, it took me a long time. I sat for at least 20 minutes, 15 minutes at least. I started looking at this diagram and I realized that this is an isosceles triangle. So it means that AB is the same as BD. So we can say that AB is the same as BD. AB is the same as BD. That's just because of sides, opposite, equal, or equal sides, opposite, equal angles. Okay, so that technically means that this could be switched out. This one can be switched out for AB. But so let's do that. Maybe that helps us. But then what I realized was that AB is also the same as AE. So AB is the same as AE. So I then switched that out like that. And AE is one of the things we're looking for, or EA, whatever. So we circle that. And so maybe we never needed this one in the first place, and it's only these four. Now, if you didn't see that, you are forgiven, because this is crazy. For 3 marks, I think the teacher who set this paper was in a bad mood, because that is just ridiculous. I mean, maybe I'm missing something here, but for 3 marks, wow. So then this looks good. We've got 4 different things over here. And so what we're going to have to do is we're going to have to do some cross multiplication. So that's, well, yeah, let's just first go write it out. So DE over AE equals to DA over DC. And then we're trying to get EA alone. So, okay, so we'll first take, there's many ways to do this. I mean, some students are really fast at this, some students struggle. So I'm going to go the slowest and the most easy method. For those of you that struggle with this, I'm first going to take the AE over. So that's going to give us AE multiplied by DA over DC equals to DE. I'm then going to multiply this DC across. So that's going to give us DE multiplied by DC equals to AE multiplied by DA. And then I'm going to divide by DA so that we can get AE alone. And there we have it, DC, DE, and AD. Okay guys, so that was crazy. For 3 marks, I don't think so. But that's how you would do that question. So you might have to watch that a few times, and maybe you didn't see it and you had to watch the video to help you, but try to gather as much information from the way I did it, so that when you get a question like that in the future, you have updated your software in your brain so you have a better, a more expanded idea of what's possible. And so 2.2.4 would be quite easy if I hadn't erased everything. So what we had was, just now we had DE, you've probably got it written down on your piece of paper, but I have to keep erasing just to clear up space. We had this just now, like a few seconds ago. And we then somehow, remember how I showed you, we eventually switched this one for EA. You might have to rewind just to remind yourself how we did that. And so if we work here, because check this out, we want EA, sorry, we're here now, we want AE squared, so that's why we have 2 there. And then there's a BC and an ED, so there we just do cross multiplication. So that's going to be EA squared and BC multiplied by DE. And so that's how you would do that question. So guys, in my opinion, I think this was a bit weird. For 3 marks for each question, I think that's a bit, I think in an exam, if I was a student, this probably would have taken me too long, and I potentially wouldn't have finished my exam. So if you wrote this paper and you found that you ran out of time, I agree. I think that was a little bit too long, and this was only part of a 1-hour exam, so that's crazy. In this question, they tell us that P has coordinates -5 and -12. So what I always tell students is make a triangle for yourself and analyze these coordinates. The -5, that's your X, so that's this one. And then the -12, that's a Y, so that's this one. You then do Pythagoras, and you would find out that this length is 13. Now, students always ask me if this 13 must be negative. That 13 is never negative. The hypotenuse is never negative. Then it says for 1 mark, can't be that difficult, determine the value without using a calculator, cos alpha. Okay, so what you do is you just remember that cos is equal to x over r, or adjacent over hypotenuse, whichever method you prefer. I like using the adjacent over hypotenuse method, and so the adjacent is -5 and the hypotenuse is 13, so that's the answer, -5 over 13. Then tan of 180 minus alpha. Now they're trying to confuse you here. You just need to know on your cast diagram that when you have the tan of 180 minus anything, so like 180 minus x, that just becomes tan x, but because tan is negative in the 180 minus quadrant, you just put a negative. So this just becomes negative tan alpha. And so now we can go into this triangle and work out tan. So tan is opposite over adjacent, or y over x, depending on your preference. And so that's going to be negative. Now the opposite is negative 12, and the adjacent is negative 5, and so that's eventually going to give us negative 12 over 5 as the final answer. Question 3.2, so we have to simplify this into a single trigonometric ratio for 6 marks. Alright, so definitely going to need the cast diagram, and then we should remember that this is sin, cos, tan, and cos. Okay, so x minus 180 is not on the cast diagram. We only have 180 minus x. So what we do, now remember the golden rule. If it is not on cast diagram, you can add or minus 360 as many times as you need to until it is on the cast diagram. So for example, the sin of x minus 180, I can simply add 360 to that, and that all of a sudden becomes sin of x plus 180. But when you plus, order doesn't matter, right? I mean, 3 plus 5 is the same as 5 plus 3. It's 8 and 8. So you can say 180 plus x. And so sin of 180 plus x is now this quadrant where sin is negative. So it becomes negative sin x. So this whole thing is just going to become negative sin x. Okay, now cos x minus 90. Now that's a challenging one. The reason is that in grade 11 we only learnt 4 of these things. Let me show you. Take you down memory lane. These are the 4 that we knew from grade 11, and these were the different answers. And here they come with this. And this little rule doesn't work with these 90 ones. So here's my advice. There is a way to change this. It's very complicated though. There's this long technique that we learned in grade 11. Not all schools were taught it. I know that for a fact. Only some teachers show it. So my advice is, you are now in grade 12. So you can actually treat this as a compound angle. Yes, one day when you start making money in your job, remember me. I just told you that. This, you can treat it as a compound angle. And if you're in a test, by the way, and you get a little bit stuck, you can technically use these compound formulas. Of course, there's the other ones that have the pluses if you need to. You can use those formulas on any of these. So Kevin, why didn't they just tell us that in grade 11? Well, they wanted you to memorize it because it will take too long if we had to go use these compound angles the whole time. But when you get to something that's awkward like this, use the compound angles. So x minus 90, and that's this one. So it just becomes cos x cos 90 plus sin x sin 90. And so that's just, now cos 90 is 0, so that just all falls away. Sin x and then sin 90 is 1. So this whole answer just becomes sin x. How cool is that, guys? We just hacked the system. And so that's sin x over there. Okay, now cos of minus x minus 360 is not even close to that. So now we can use this rule. If it is not on the cast diagram, add or minus 360. This one we're going to have to add. That'll work best there. So we can say that that's going to be equal to cos of minus x minus 360 plus 360. And that's just going to cause the 360s to cancel. And so that's going to give us cos negative x. Now, still not great. So what we do now is we can add 360 again. Now when you add, the order doesn't matter, and so that becomes 360 minus x. Now that's on the cast diagram, and cos is positive in that quadrant, so it just becomes cos x. So this would eventually just become cos x. Now this is a co-function, which I showed you just now. Remember I showed you the 4? But if you ever forget, remember, use the compound angles. Alright, so just use the compound angles as I just said, and it'll be fine. But if you do memorize it, or if you have memorized it, you would know that this one just becomes cos x. And so if we go rewrite everything, we're going to get negative. Sorry if you hear my dog in the background. She seems to bark at certain times. It's so annoying. And then the next part became sin x. And then at the bottom here, we've got cos x and then cos x. Okay, so we're going to have at the top negative sin squared x, and at the bottom cos squared x. And so sin over cos is tan, and so if you have a square, that's okay. It just becomes negative tan squared of x. Alright, so this question is more of like a proof, and it's quite weird, but it's not that long. So let's see how it goes. So they tell us that this is true. Now we know that this is true. It's one of the compound formulas, and it says use that identity to try and make something for sin of a plus b. So what we do is we say sin of a plus b is the same as cos of 90 minus a plus b, right? That's a cofunction. That's like saying that sin x is the same as cos 90 minus x. So now I just said that sin of a plus b is the same as cos of 90 minus a plus b. You might have to just pause and think about that a bit, but that's just a cofunction. Now, where some students get confused, and I've done this before when I first had a look at this, is you might want to go do the this formula on this now. And what that would give you is it would give you cos 90, cos a plus b, plus sin 90, and then sin a plus b. And then cos 90 is 0, so this whole part just falls away. And then sin 90 is 1. But now this doesn't give us anything useful. We just end up with sin of a plus b equals to sin of a plus b. Mathematically, there's nothing wrong here, but it doesn't achieve anything. So what we're going to do is, like a little trick, is we rather want to do it like this. We know that 90 minus a plus b is the same as 90 minus a minus b. And so what we do is we put these two together. So we say, let's put those two together and then have it like that. Okay, so this part here, the 90 minus a, is almost like this part, and then this part here is that part over there. And so now what we can do is use this formula, and so that's going to go cos 90 minus a times cos b plus sin of 90 minus a times by sin b. And cos of 90 minus a is just sin a, it's a cofunction. Cos b is just cos b. Sin of 90 minus a is times by sin b. And so there we've derived a formula for that. So if you did it this way, it's okay, it's not wrong, but it's not going to get you anywhere. So what's better is to rather just regroup the angles in a slightly different way, and then it gets you what you want.